Hi, my name is Omar Francisco. This is my final project for the Introduction to Deep Learning class. My project is an object classification neural network trained to classify resistors. This project is limited to 3 types of resistors with the values 7.5, 15, and 22 kilo ohms. After proving success, the number of resistors can be augmented as needed. The hardware to capture the images is a VHO VMS004 electronic microscope. This is an old model, and newer versions have better optics. This is what I had at hand, and it should fit the bill. Because of the close-ups required to capture good images of a resistor, using a webcam is not an option. The computer I am using has an Intel i7 CPU with 4 cores running at 3.8 GHz. The GPU is an NVIDIA GeForce GTX 970 with 4 GB of RAM. The first step is to create a virtual environment and install all the packages needed to support the project. This will provide an isolated environment that can be modified without affecting other projects in my computer. The next step involves capturing the images. To capture the images programmatically, I could have used OpenCV, but instead I opted for the software that comes with the VHO microscope. It provides more control and allows vertical and horizontal image flip to facilitate positioning the resistors under the microscope. The next step is to label the images. For this, I will use an open source image labeling application from GitHub. This application allows drawing a boundary around the target objects and creates an XML file with the coordinates. The next step is to split 80% of the data for training and 20% for validation. After the data has been split, I will use an open source utility to generate TensorFlow records. This facilitates input into the model and allows me to work with 2 files, one containing all the training data and the other one all the test data. The next step is the installation and configuration of one of the models for object detection from the Google Model Zoo. I tried a couple of models and settled for the one that gave me the best validation. Trying multiple models is easy once the pipeline has been configured. After training the model, 2 types of tests will be performed. First, I will classify the test images which have not been seen by the model. Second, I will classify resistors from a live feed and see how the model performs. To conclude, we'll look at metrics generated during training and testing and discuss opportunities for model improvement. Needless to say, I am stepping on the shoulder of giants. I am leveraging a great deal of information from YouTube and GitHub to make this project possible. The URLs for all of the utilities and models are documented in the presentation distributed in class, as well as in the description of the video. Let's start cooking. The creation of the virtual environment follows the Python convention. Since this is something that should be done for every project, I have created a batch file to assist. The batch file takes the environment name as a parameter, creates and activates the environment, and prints additional steps to upgrade pip, install a kernel, and make that kernel available to Anaconda with the same environment name. Once done, we are ready to start capturing images. Let's launch Jupyter Notebook and load the image collection and labeling notebook. OpenCV and PyQt are required for the application that labels the images. A folder to store the images for the 7.5, 15, and 22 kilo ohms resistors needs to be created. Extending the proof of concept to additional resistors require adding them as part of this list. After creating the folders, we are ready to capture images. Capturing the images with the VHO software is easy. First, let's select the directory for the target resistor. Then, let's take pictures along the capture area, each time moving the resistor a little bit to the opposite side. This process is repeated for each of the resistors. Before I start labeling the images, let's tidy up the image names by sequentially naming them. The script in this cell walks all the folders where the images are stored and renames them sequentially. Now, let's launch the labeling application. Let's open the 7.5 kilo ohm directory and load all the files. Let's create a boundary around each resistor, one image at a time. Let's give the boundary a label name. The label name is case sensitive and will be used during training. Let's save the label file, which is an XML file that contains the boundary and label information. This process is repeated for every image in the folder. After completing the labeling process, 80% of the images and their corresponding label files are moved into the training folder, and the remaining 20% are moved into the eval folder. To train the model, let's launch the Training and Detection Notebook. Multiple libraries are required to support the workflow. The model's name and model URL reflect the model I choose to download from the TensorFlow Model Zoo. A view path to support scripts, images, and the overall TensorFlow Model Zoo pipeline needs to be configured. The label map with the resistor label together with the train and validation TensorFlow workflow records are created. This is how these files look like after creation. The images and label files are aggregated into a single train and test file. Finally, we get to the pipeline.config file. When I started this project, I erroneously assumed I would be constrained by a pre-trained model, but that is far from the truth. Opening the pipeline.config file gives me the opportunity to introduce many of the concepts learned in class and tweak the model as needed. For instance, resizing the image as it is fed to the model, controlling weights, activation functions, loss normalization, batch size, and data augmentation options. In this case, the image is getting cropped. If additional operations such as rotation or magnification are needed, they can be added in this section of the pipeline. This approach to consuming a model is more efficient than creating a model from scratch. It allows swapping models in and out of the pipeline and provides a solution that can be easily reused and augmented. Last, we're ready to train the model. This is the command used to train the model. The training will go for 2000 epochs, and then we are ready for validation. This whole process in my PC took about 50 minutes. To validate on-scene images selected for testing, let's first load the model from the last training checkpoint and then load the list of images to test. Out of two images of 7.5 kilo ohm resistors, one was not classified, but the other was classified with a 83% confidence. Out of two images of 15 kilo ohms resistors, one was misclassified as 22 kilo ohms, and the other one was classified accurately with a 99% confidence. Last, out of two images of 22 kilo ohms resistors, both were classified accurately with a 98% confidence. The classification has not been perfect, but very encouraging. Let's see how the model does detecting a real-time feed. Let's load the live microscope feed using OpenCV. Let's test the 7.5 kilo ohms resistor. It is classified with 90% confidence. Let's test the 15 kilo ohms resistor. It is first misclassified as 22 kilo ohms and then classified accurately with 99% confidence. Let's test the 22 kilo ohms resistor. It is classified accurately with 98% confidence. TensorBoard, which is distributed with TensorFlow, captures interesting metrics. These metrics let you see the overall performance of the model during training and the model's ability to detect object boundaries of different sizes during validation. In conclusion, the still image classification would benefit from additional pictures since not all the images were detected successfully. One feature I could not figure out how to program in the pipeline is early stopping to minimize overfitting. I will need to do additional research to understand how this is done via the pipeline config file. This project would benefit from a better microscope that provides better colors for the different bands of the resistors. This would open the door to use higher resolution models, which are slower but with higher accuracy. Signing out, Omar Francisco.